How's everyone doing? I hope you guys are doing well. You guys have, it's honestly, it's fantastic. Thank you, Angela. Great to hear from you. I know this stuff ain't easy, man, and it's probably about as dry as a cracker. It is. But where you guys are going, nursing, vet techs, paramedics for sure, firefighters for sure. This chemistry, you gotta have it. You gotta have that foundation in there. And yeah, it's all good, Jennifer. You're doing great. The I know it's tough, and it's tough that you guys are there, but I know it only looks this way. But you guys are doing really great. The people who have emailed me, I love it. I love it. And some of you guys have emailed me like 10, 15 times about this or that, and I love it. I don't ever want you guys to feel that you're bothering me. Okay? The whole adage there, the squeaky wheel gets the oil. And I'm not a mind reader as much as my wife thinks I am or wishes I was. I love her. She's just getting ready for work. I can't read your minds. I can't tell what's going on unless you tell me. All right? And yesterday, I think it was yesterday, the days just kind of blend, don't they? Here we are again. What is it, week 5? Week 12? I don't know. But the meeting there we had yesterday, little team meeting. I had the one there for my physics and my chem. You guys there. Oh yeah, week 1 does. I know, woohoo, week 12. Who was I chatting with there on email? You know what I mean? And I know one person emails me about a concern. I know that there's 10 of you out there, okay? And with the same feeling. And I know this stuff can get beastly at times, all right? But it's all about organization. You guys have your formula sheet, and I'm going to show you that there today, and it's all cleaned up, and it's nice, ready to go, and that's it. All right? But you wouldn't be the first person to say that I absolutely hate this stuff. Okay? And it's all good. You guys know you guys need it in order to get to where you want to go. That's why you're dealing with me in the first place. Okay? But wait until you get to, if you absolutely disdain this stuff, man, you can't handle it. All right, good. The wait until you get to week 8. Organic, to me anyway, is fun. There's no real calculations anymore. It's about propane molecule, carbon, carbon, carbon with hydrogens all around it, as compared to octane, which is carbon, 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 carbon. I think there's 8, and then hydrogen. And it's more spatial. It's diagrammatic. It's visual. It's 3D. You can flip these molecules around in your mind because, and we're going to watch videos. It's more spatial. It's better. I can't say it's better. It's different. It's more artsy. It's more creative. This is more the scientific side, the mathematics side. So, yeah. You will need this stuff. Nurses, paramedics, doing dilutions, M1V1, M2V2. You might as well get that tattooed on your shoulder. Well, you can't read it on your shoulder, so maybe your hand. Don't get it tattooed. I'm joking. All right? But, you guys are going to be doing that literally 150 times a day. All right, cool. Cheers, Aaron. So I just wanted to touch base with you guys yesterday, and I didn't teach anything. I just wanted to know how you guys were doing. So I just wanted to know how you guys were doing, and the people who showed up, I appreciate it. Some people emailed me and said they couldn't show up, but they wanted to show up. Love it. Okay. We're here. This is regular class time. So I hope you guys are all here. And thank you guys for coming. This will be the last lecture where I'm sitting here with a PowerPoint giving you new information. Okay? Like what was it? Week 1 was review of 1008 Chem. Week 2 was solutions. Week 3 was what? Acid bases. Week 4 was chemical equilibria. And there, this week 5 is gases. And long millions of years ago, I used to teach this course over a 6-week period, but it's heavy, man. So, if I'm gonna force, force information in your ear, well, I might as well force more of it in your ear so that we have an extra week off. So, next week. Yeah. Oh, I hear you. Next week, we're gonna have a class, but it's review. And honestly, these are the most fun classes for me. I'm just trying to think of how I could do it live, because this is like the real test of me as a teacher, where I give you guys a review package, and it's hang on. I give you there's a review package that's going to come on out, and I don't know, it's 2, 3, 4, 500 questions. I don't know, it's a beast. All right, and I just give that to you guys, and you guys just whack-a-mole, hit it. And week 6 is usually my funnest week, because you guys can hit me with question 196, 169, number 3, and I got to know everything, and I got to be able to. So I'm going to try and work on that so that we can have some type of a workable review. And so next week we'll have class time during this time. In what mode, I don't know. I'm conjuring and I'm creating on this side to try and make it a little better. But the general feeling there I got from the people who came to the meeting there yesterday was that things are okay. Things are heavy. But the good news is this is it. And thank you guys for coming, man. I couldn't imagine someone... we're going to record this, so there's going to be lots of questions and that you guys are going to ask on the recording for people who can't make it to the class there today. But this one here, it's not really new. You'll see. We'll be here for 2 hours. That's what I'm thinking. We'll see. I don't know. I've been overestimating my time there. So maybe we won't be 2 hours. But today's a good one, and this is it. Okay. It's an off week for you and me. You guys have done stellar. You know what I mean? 2 quizzes. You guys have your assignment due. I don't know, was that due there at noon, or was it due? I think it's due at midnight. And so get on it. Keep cracking, man. Keep cracking. And now is not the time to let your foot off the gas. Don't do it. We're 5 weeks in. This is it. Next stop is the exam. Okay? Hopefully there by, I don't know, man. I'm going to shoot for Saturday or Sunday or somewhere in there. I'll have the review package out to you. All right? And it'll have the answers on it. So now, am I going to pull my information from that? Generally, yes. Any questions specifically from that? No. But that'll give you the idea of what we're looking for there. The test will be in 2 weeks today. The test will open, I'm assuming there at this time, 1 o'clock. And I'm thinking there that I will leave it open until like 10 o'clock. All right, so that gives you, I don't know, we're just talking right here. It'll be in that range, so it won't be a 3-hour or 2-hour beat down time test. Okay, because I know that people have jobs and kids, and I got 2 of them downstairs who will probably interrupt us, so be prepared. But they're as cute as a button. But that's what we're looking at. Everything is coming down to this. And I see your comments there. I'll get to them there in a second. But just keep plugging away. Do not lose faith in what you're doing. If something isn't working out, do it twice. Email me. That's all you got to do. Okay? So you just keep on it. Keep at it. Are there any immediate concerns of anything? Are there any emergencies that need to be addressed at this time? If not, we can hold on there till the end. I'm just going through the chats here. Klingon and Vulcan. Yes, I know them well. Kapla. Wait, what? They test 2 weeks today. Okay, and I'm assuming there that I'll open it up at 1 o'clock and I'll close it there the same day. It won't be an elongated test assignment kind of a thing. It'll be open for like 7, 8, 9, 10 hours, something like that. We'll see. If there's any issues, if you have anything going on, you need to let me know, like now. Okay, if people have some type of accommodation, I'm aware of those ones. But if there's anything above and beyond that you need, talk to me first now, because we have 2 weeks to formulate. Okay. I don't see any. Are we able to run it off or just? Okay. Yeah, I like giving you guys. I think you remember the first quiz we did there with the emailed quiz? No more of that. What I kind of like to do, and this will be my new thing here, is I'll give you guys an assignment or whatever, and you guys have a paper copy that you guys can toot around with there during the week and work on it, and then you guys can input your answers there. I kind of like that style, and I think that we'll continue with that. Because I like people having paper copies if they so choose, and some people just like the e-copies. Away you go. So it's all good. Okay, I will continue, and if you guys have anything to add, let me know. But I think you guys are doing great, and believe in yourselves. I don't know, man. I don't know where along the line people lose their confidence, but do not. I believe in you. Get this done. Okay? Get it done. Get your A. And even if you don't like this stuff, you don't have to like it. You know what? But at least you'll see there that the course is designed as where you make your money in these courses is the labs. Those labs are 4% each, or whatever they are. They could be 3%. I think they're maybe 5%. Sorry, I've got 5 different classes. So that's where you make your money. Okay? Never miss an assignment, all things. If you guys can just do your labs, do your assignments, and do your quizzes, you've already passed the course. You don't even need to do the test. I don't think, if you get 100 and everything. So that's where we're at. So if you don't like this stuff, it's okay. Just get it done, get your 70, and get over to the next half of the semester, and then get your 95, which will average out to be an 85 average, which will take you anywhere as long as I need, as long as I know. But anyway, Ian, shut up. Let's go. Share screen. Let's go. Gaseous states of matter. All right, this is what we're talking about here. Today it's only gases. And gases are a strange one. Like a solid there, you can't push it, right? A solid is, you can't, it is what it is, right? And liquids, like hydraulics, when the digger raises, 5,000 kilogram car or whatever, right? It's all hydraulics. You can't really press them either. Liquids, you can't press them. But gases, you're going to see there that there's a bit of, they're a little different. They have an indefinite volume. Okay, they will always expand to fill the container. All right. They have an indefinite shape. They'll take the shape of any container. You have some fancy watering jug that goes like this and all this, with the gas is all in it. All right, takes the shape. And they have very low densities. And that's a formula there that we're going to be talking about as well there today. But the density of water, you guys should know this. 1 gram is equal to 1 milliliter. So 1 milliliter of water weighs 1 gram. 1,000 milliliters of water, which is a liter, weighs 1 kg. All right, so that's kind of the standard there when we're talking about density. But you look at the density of air, okay, it is very much 1.2 grams per liter. So it's like on a scale of 1,000 times less dense than liquid. Kinetic energy. Anybody know what kinetic means? It means motion. And you look at this pen. Okay? I'm holding it in my hand and it doesn't look like it's moving, but it is. Okay? It's a solid. Liquids and gases will all be moving. If anything is in existence, that means that it has energy in it. Only at absolute zero, minus 273.15 degrees Celsius, do the atoms stop vibrating. Okay? Anything above minus 273.15 degrees Celsius, you get they're moving. Why are they moving? Because they have energy. Kinetic energy is motion, moving energy. And so you have a block of ice, it's vibrating, but then at 0 degrees Celsius, what happens is these things are vibrating. This is ice at 0 degrees Celsius. It's vibrating so fast that all of a sudden, pachoom, a water molecule pops off like popcorn. And then another one, and then another one, and then another one. And that's how we get a liquid. These guys here, these atoms are now moving now. At 100 degrees, the same thing happens from liquid to a gas. You get this popcorn effect. And now these guys are a gas, right? Please have a note of this. I promise you I'll have 2 or 3 questions on the test about this. This is mucho bueno importante. Okay? Sorry, my Spanish. I don't speak Spanish. I didn't mean to offend anybody. But kinetic molecular theory, KMT. There's a lot of assumptions that go on here with this. That gases consist of tiny particles. Okay, so you have O2. 2 oxygen atoms come together to make an oxygen O2 molecule. Oxygen has a molar mass of 32 grams per mole. 16 and 16, 32 grams per mole. Hydrogen, H2, is a hydrogen and a hydrogen. It has a molar mass of 2 grams per mole. But according to the kinetic molecular theory, the one molecule of hydrogen, H2, is equivalent in mass and all this kind of stuff. We take it as such that these two guys are the same, even though this one's 32 grams per mole, this one here is 2 grams per mole, and they exist in space kind of the same. Because you think about this, point number 2, the distance between these particles is enormous. Like here we're talking a couple of atoms. Like I got maybe 2 oxygen, I got an oxygen molecule over here, O2 over in the corner, and I got another oxygen molecule over here. You just look at how small they are and how big that distance is. It's like travel. It's like me being here on Earth and somebody else being on Jupiter. You know what I mean? It's just an astronomical distance. So the distance between particles is large between each of the small particles. Gas particles have no attraction to each other. Okay? They are considered the same size in all fairness. Gas particles move in straight lines in all directions, colliding frequently with each other and the walls of the container. So I just blew up my son's balloon there about half an hour ago. Why is the balloon this big? Because the molecules on the inside are holding it up, right? They're creating an air pressure on the inside that's holding that balloon up, okay? KMT. Number 5 there, these collisions are perfectly elastic. Great word, you'll need it there in physics if you're doing momentum anytime soon, okay? An elastic collision means no energy is lost in the collision. and we assume this. And generally there isn't. If an oxygen molecule hits another oxygen molecule, like a cue ball hitting an 8-ball there on the pool table, they transfer electricity, but none of it is lost, which is kind of theoretically impossible, but things happen strange on the quantum nuclear level. And what I mean is quantum. I don't know if you guys have ever seen Ant-Man, and where I think his boss, or was it his boss's wife, she shrunk down to the atomic size, and she's been there for 20 years. They speculate there that time is, Einstein's theory of relativity, time is relative to where you are, and there really is no time at the quantum atomic level. Weird things go on. So for all intents and purposes, collisions are perfectly elastic. There is no energy lost. Average kinetic energy for particles. Oh, you'll see this one there next week, I think, in my physics class. Kinetic energy is equal to half the mass times the velocity squared. Will we be using this in this course? No. But I just wanted to show you there that there is no such thing as independent chemistry and independent physics, or independent biology, or independent math. They're all the same thing. They really are, of all the one thing. Science. The average kinetic energy is directly proportional to the Kelvin temperature. So if you increase the temperature, these things get out of control, right? You get the popcorn effect. So you increase the temperature, you increase the kinetic energy. Great word here. Another word. We'll just go through some definitions there first. Diffusion. Here I've got a flask here with only bromine gas in it. And over here I've only got air, and it's closed. Well, if we open it up, things move from a high concentration to a low concentration. And when I don't know where you guys are at in your biology. You guys are week 5, or probably into the heart somewhere. I don't know when you guys get into respiration. External respiration, breathing with your lungs, or internal respiration, intracellular respiration when you're breathing in your big toe. But the whole idea of diffusion, oxygen, which is 21% in the air, will move readily into the bloodstream, okay? And carbon dioxide, which is high in the bloodstream, will move readily out and into. So it's all diffusion. Great word. You'll see that again there in your bio for sure. Atmospheric pressure. This right here is, and I come back to this because we'll be doing some calculations with this. Getting back into, you remember the balloon, and the air is holding up the balloon. Well, it happens for everything. Like you look at this glass of Coke Zero, right? Like, what is keeping... Gravity is keeping this thing down too, but there's also air pressure as well. And how do you know that air pressure exists? What is air pressure? Well, I have the piece of paper, Nothing, just piece of paper. All right. And if I blow down on this piece of paper, it should go down, correct? Well, all right. So here, I've got my piece of paper, and I'm blowing down on it. Hey man, that's not right. Let's try this again here. It went up. Interesting. And the air, the molecules there, the gas in the air, they're moving around according to the temperature. And before I say this, temperature isn't what you think it is. Temperature is an average reading. Like in here, it's probably 20 degrees. But there's a molecule over there, oxygen, that I see is 27 degrees. And there's the carbon dioxide molecule over there, and it's 17 degrees. Everything will have its own temperature. A temperature is an average, though. If I say at 21 degrees in here, it's an average temperature for a given area. But the more temperature, the more you increase the temperature, the more the kinetic energy. This is one of the things here when we're talking about atmospheric pressure. Pressure is everywhere. It's pushing on me, it's pushing on the computer, it's pushing on everything. All right? If this was water, okay, and we're down here on ground level, the atmospheric pressure is pushing down on this water, or this Coke Zero, which is 99% water anyway. The boiling point of water is 100 degrees Celsius here on the Earth's crust, or at sea level. All right? But if we go to the top of Mount Everest, you see, now, you see, air pressure is just like the ocean pressure. If you go down to the bottom of the ocean, you'd look like a can of Coca-Cola. Okay? Because you think about it, you would have 5 kilometers of water pushing down on you. Hundreds of millions of tons. You know what I mean? That's what we're talking about, pressure. And you see here, we're at sea level. Actually, we're not. We're far from it. But we have, 20 kilometers of air pushing down on us. Okay, it's air. I'm okay with that. But it still is exerting a force. And it's the same force that's keeping this down. But if I go to the top of Mount Everest, I don't have that 20 kilometers of air on top of me. I only have 12. Because Everest is 8,000 meters. The air pressure is less. And so you'll see there that water actually boils at 71 degrees on the top of Mount Everest. And it's this idea of air pressure. And I don't know if you guys have really covered this there before. That's why I'm kind of taking a bit of time with it. And this lecture is going to be a bit of a long one. It should be anyway. It's the final one. But the whole idea of air pressure is when we can use it in these calculations here, and it affects chemistry. Because if you have a balloon at a certain temperature, and it's this big because the molecules on the inside are pushing it out, right? Because they have this energy, because it's 23 degrees in the balloon, those molecules are moving side by side and they're hitting the inside of the wall and they're keeping the balloon looking like this. Well, take that balloon and put it in the fridge. So this balloon had a volume of 5 liters at this temperature. Well, if you put it into the fridge, what's going to happen now to the gas inside that balloon? It's going to contract, and then your balloon is going to be this big. So these are just some of the things here that we can manipulate pressure with temperature. And we'll get into all this. There are 3 ways to talk about pressure. One is the scientific way. So on a normal sunny day in July, 28 degrees, beautiful day, the pressure is 1 atmosphere. And what that just means is Earth has an atmosphere of pressure, and we live here, so we're going to take this as the standard 1 atmosphere. Old school American or UK, they will use what's called the torr. And it was all based on this guy here. He had mercury in a tube. And you see there the air pressure is holding it back, pushing on it, and actually pushing it up the tube. And on a nice normal sunny day, the air pressure was 760 millimeters of mercury. I'll go over this all again. I'm just kind of foreshadowing. The SI way of talking about pressure is kilopascals. Okay? And a normal sunny day is 101.325 kPa. These all mean the same thing, and we'll come back and talk to this. But getting back to this, why did this go? It's for the same reason that on a rainy day, a hurricane or tornado, a cloudy day, rainy, that kind of a day, the pressure goes down. Fast moving air, rainy days means low pressure. Okay? Sunny days, no wind, high pressure. So look what's going on here. Where is the low pressure? Well, where's the fast-moving air? It's on top. So that, like this piece of paper here has the same pressure right now on both sides. So that's why the paper is just sitting there like this. But if I have wind coming on one side, now the low pressure is on the same side as the wind. The other side, which is not experiencing any wind, still had the same pressure as before, but because this side is lower, now it pushes. It's the same principle behind an airplane. What do you think drives an airplane? The engine makes it go forward, but it's the wing design. You see, the fast-moving air goes over the top of the wing. The slow-moving air is on the bottom of the wing. So the bottom of, a 70,000-pound airplane gets lifted up by air. Whacked. Let's move on. Now, here's your first mathematics. Rock and roll. It's all based on this right here. Air pressure. We've got to be able to convert from atmosphere to torr. And torr means millimeters of mercury. You'll see me refer to those two interchangeably, okay? And kilopascals. Because I could give you a question with atmospheres, ask you to change it there to torr. It's all good. So how do we do this? Let's go. Convert, don't move it, convert 765 millimeters of mercury to atmosphere. So I want to go from millimeters of mercury to atmosphere. Well, what I do is I just go like this. Okay? And you see here now, something like this anyway. And now, see, we're not talking about kilopascals, so get it out of there. It's not involved. So now I'm dealing with this over this. Plug and play, where you just do across, you're basically just doing a box. So you fill in what you know. Well, you got 760 millimeters of mercury is equal to 1 atmosphere. Bang, bang. What am I asking it to do? Keep your millimeters of mercury together. Keep your atmospheres together. There's your X. Cross multiply, away you go. Let's try another one. Convert 775 millimeters of mercury to kilopascals. So it just so happens there that, here I have one box here. And I got another box here. So now, this is what they're asking you to find. Okay, so let me know if that's an issue. It's just simple ratios. Okay, and you keep your units together. All right, and solve for X and away you go. So in this case here, 775 millimeters of mercury is equal to 103.3 kilopascals. This one here is on the, you'll notice here that I've added an extra triangle there to the week 1 because you'll kind of use it with these guys here. And so it's a triangle formula. There's your density. That's there. That's a new one. And right here. Yes, 1 atmosphere is equal to 760 is equal to 101.3. So it's here for you. You don't have to memorize it. Okay? Okay. And again here's another question. A pressure of 3 atmospheres is equal to, so basically 3 atmospheres. This is 3 times the pressure that we feel on Earth normally. All right? A pressure of 3 atmospheres is equal to, which one does it equal? And you just set up your ratio. We're not looking for kPa. Set it all up. Away you go. Okay? Feel free to interject if I'm going too fast or you're not getting something or if I'm just completely inaudible. Dependence of pressure. Now, we're going to talk about a number of things here. We're going to go back to moles. Oh, yeah. We're going to talk about pressure. We're going to talk about temperature. And we're talking about volume. Yes. What do we got? Where are we? Hello. Who am I speaking to?
You're talking to Jen Searson.
Good.
Someone asked a question in the chat saying, would the answer not be 99.3 for the last slide instead of the 103.3?
Honestly, it very well could be. What do we got here now? What, you talking about this one here? Jennifer? Is it this slide here?
I have no idea. I'm asking for someone else in the chat.
Here, let me stop sharing. What, is it in the chat?
Sorry, Ian.
No, sorry. What do we got?
It's for slide 7.
All right. It could be, so...
Unless I'm doing it wrong.
No. Let's have a look here. Which one? I do these late at night because they're really can't. Let's 760 times. So 7. No, that first one looks good. Divided by 775 divided by 760. Yeah, the first one is good. 88 millimeters, or sorry, 88.888 atmosphere. And the second one there, what do we got, is 101.3 times 775 equals divided by 760. 103.3.
Okay, so do you divide 775 by 760?
Ah, yeah, these boxes, they're kind of, I don't want to say they're exactly the same, but they are. They're for completely different purposes, but they're exactly the same as the boxes there we did week 1. And it's just a ratio, right? And let me see if I can insert... hey, man, where's my double arrow? There it is. And so, yeah. And you see what you do. Like you multiply this guy by this guy, and then you multiply these two guys together and solve for x, right? It's exactly the same as we did there for week 1. Okay?
Right, okay.
Is that cool?
Yeah, thank you.
No, it's all good. Hey, man, that's what we're doing here. And I know I'll take minute, 2 minute, 10 minute. So, and if there are mistakes, like I'm sure there's at least one. But that's how you do these guys. Okay, cross them up, solve for x. All right. You're going to start. What was I saying there? Moles, pressure, temperature, and volume. There are relationships going on all over the place, and we're going to get into them there. Where the pressure is proportional to the number of molecules, and you're going to see N used here. All right. The increased pressure is due to more collisions in the wall of the container. So hold on here. Let's say I have a balloon, 5 liters. And let's say there's 2 moles of gas in there. What happens if I increased the pressure? All right? Like or if I increase the pressure, what's going to go on to my volume? It's going to go down. And you look, all these molecules that were in here at 5 liters, they were happy, they were moving around, they were shaking, they were going to the store, they were doing they were having a great time. But now all of a sudden I put them all into a 1 liter balloon. They're not happy. They're angry. The pressure's up. It's the same thing if I had a room full of people, 20 people in the living room. Okay, everyone's doing all right. Everyone's got elbow room. But now I say, all right, 20 people, everyone in the bathroom, let's go. It's going to be a problem, right? You've now increased the pressure. People are going to be, and so there is a relationship here. And I want to show you guys. And it's kind of the same thing here. You have these atoms in here and they're happy. And if I decrease the pressure or increase the volume, say I'm increasing the volume, I'm making the space bigger, these guys are going to have more room. So the pressure has been less. All right. Have a look here. If I decrease the volume, you can see there now that I've increased the pressure. we'll get into all these guys there. I don't know if you guys are familiar there with Boyle's Law or Charles' Law. That's where we're going. Yeah, have a look here. Pressure is proportional to temperature. And here you have this at, I'm just trying to read that. This is at 2.24 atmospheres at 0 degrees Celsius. So these guys, this is at 0 degrees. The pressure here is 2.24. But then if I kick the temperature up to 100, look at the pressure now. It's at 3.06 atmospheres. I've increased the pressure because now these atoms or molecules in the system are now moving around faster. So now they're hitting the inside of the container or inside of the balloon faster and harder. So therefore now the pressure has increased. More collisions, higher energy collisions. So there's a relationship there as well. Don't worry if you're kind of, okay, what's he on about? It'll all come together. I got it all coming up. So have a look at this one. Really no mathematics, just more of a comprehension question. If you change the temperature of a sample of gas from 80 degrees Celsius to 25 degrees Celsius at a constant volume, so you kept the volume the same. So it didn't go from here to here. It's not a balloon in the freezer question. Let's say the balloon is a ceramic balloon at 80 degrees. And now it's still a ceramic balloon, didn't move, at 25 degrees. What's going on inside? What are the atoms doing inside? What's going on? The pressure will decrease. If you're decreasing the temperature, you'll decrease the pressure. But don't worry about this. It's all coming all up here. I'll explain all this stuff there, and by the end of this, you guys will be fine. Here's equation, Boyle's Law. P1V1 is equal to P2V2. And what will happen to the volume if you double the pressure? And if you have a look here at this right here, I wonder if I can just kind of blow this up and have a look at it. Here, this is pressure. So the pressure is increasing. 1, 2, 3, 4, 5, 6. Crazy pressure. And here the volume is increasing. 1 liter, 2 liter, 3 liter, 4 liter. So you can just have a look here. If you're increasing the volume, you're giving the atoms more space to run around. So what are you doing to the pressure? Increase the volume, decrease the pressure. Increase the volume, decrease the pressure. Look at this one. If you increase the volume, I know it looks weird, you're increasing, but the volume's getting smaller, not the pressure. If you increase the pressure, then you are decreasing the volume. Boyle's Law, this one here, works in an inverse fashion. If you increase the pressure, you're decreasing the volume. If you increase the volume, you're decreasing the pressure. Okay? So oh yeah, you'll see that one there. But these formulas aren't bad. What am I going to do with these formulas? How many parameters or how many unknowns are in this formula? 4, right? Well, I'm going to give you 3, and you find the 4th. Woo. That's all these are. I'm going to give you 3. You find the last one. And here's an example. Do I have animation on here? I have some animation on some of these slides because towards the end, man, there's a couple there that are kind of oof. All right, but have a look here. A sample of argon gas occupies 500 mils at 920 torr. All right, so what you're doing is you're pulling this stuff off to a piece of scrap paper. Okay, volume, 500 milliliters. Pressure, 920 millimeters of mercury and 920 torr. Calculate the pressure of the gas. So we're looking for pressure if the volume is increased to 937 milliliters. Okay, so hopefully there you guys have seen that dealing with these, we call these the gas laws. And there's 3 or 4 of them here that we're going to cover there today. Basically, you're talking, it's kind of like dilution 1 and dilution 2, right? You've got scenario 1, you've got a solution there, 0.4 molar solution, 300 mils, and I dilute it. All right, and situation 1, situation 2. Kind of the same thing here. You've got the balloon at an initial volume, and what are we? I'm looking at my 500 milliliters at 920 torr. Calculate the pressure of the gas if the volume is increased to 937. So you've increased the volume. What's going to happen to the pressure? Please be able to, in some fashion, anticipate your answer. Don't blindly just, okay, the calculator told me this, and that's the answer. You guys are better than that. Anticipate what direction your answer is going to be in. So I got 500 mils, 920 torr, and I'm increasing the volume. So what should happen to my pressure? Should tank. And it does. So these guys here, P1, V1, P2, V2, you're only dealing with pressure and volume in the question. The question is asking you for pressure. You find your formula. This is it. Plug and play. That's all these are. Let's go. Same question. Y'all can follow it from here. Okay? It's exactly the same question. This I promise you will be an exam question. I'm just going to change this one, and this one, and this one. Did I just say that? Darn it. Here's another one. Okay, a 400 milliliter sample of gas is at a pressure of 760 torr. If the temperature remains constant, I'll put that in there to trick you. You're thinking temperature. Hey, wait a second, temperature. But you see how in Boyle's law, there ain't no temperature. Here we're only talking about pressure and volume, and they work like this. All right? That's how you tell these questions from another. So if the temperature remains constant, what will be its volume at 190 torr? Well, there's your volume, 400. There's my initial pressure, 760. I'm dropping the pressure down to 190, so I'm tanking this thing by a whole bunch of pressure. So my volume better be up, way up. And if you do the calculations there, you actually get 1.60 times 10 to the 3 milliliters. Okay, what's that? 1.6 liters. All right. So try these out. We're moving on to another gas law. This is Charles' law. And this one here is kind of cool in the fact that it involves temperature. And this whole process, what this person did was they started they started to extrapolate, they're cooling things down and measuring the amount of kinetic energy there that they have. And of course, we can't, I think this was done back in the 18th century, 17th century. And you know what I mean, there's no computers or anything like this, right? So the amount of scientific technology that this person, Charles, would have had is limited. But still, this person is measuring the kinetic energy via the temperature. And okay, things started to, we're cooling it down and we're starting to get these graphs here. And, the best I can do is take it down to -5 or whatever. And, but you do this for methane, you do this for, whatever, all these different kinds of compounds. And you start to notice that they're all, this one here is going like this. This one here is going like that. This one here is going, but they're all kind of going in the same spot. And it's one of the things there that we don't really truly understand, but we just take it as fact. That all these things, you start to cool them, And they all, eventually, they're aiming for minus 273.15 degrees Celsius. Now again, negative 273 degrees Celsius. Absolute zero, where the atoms theoretically stop. We can't hit it. We know where it is. It's out in between Jupiter and Saturn. Out there in the middle of space, where there is nothing, it is minus 273.15 degrees Celsius, or absolute zero. But you see how they've got these dots here? We'll never get there, because if I get in my spaceship and go out into the middle of Jupiter and Saturn, and I got my thermometer, and I'm out there in space, and I'm floating in space, okay, man, hey, this is showing minus 243 degrees. Where's my mind? Because I have brought myself. I have brought my thermometer, which has mass, which has energy, which has heat, temperature. So therefore now I'm affecting the nothingness. All right? But anyway, just a little bit of background there. If you are watching this from YouTube, it's pre-recorded, you might want to fast forward that section. Okay, good enough. Here's another formula. Charles' law. Volume over temperature. Now, you're reading these questions here on a test or whatever, and you never know, every question that you just finish, you go on to the next one, you kind of have to reboot, because you never know. It's just mashed potatoes, right? Week 1 to week 4, back to week 2 to week 5. So you're looking at this going, okay, what's he going to throw at me here? I got a 2-liter helium balloon. Okay, so there's a volume at 25 degrees Celsius. Okay, there's a volume and a temperature. Is taken outside on a cold winter day to negative 15 degrees Celsius. Oh, I got another temperature. What is the new volume of the balloon? So here, I've given you 3. You give me the 4th. Same banana. Okay? The only trick to Charles' law. The only trick. Write this one down. Do not forget. I will give you this in Celsius, but you have to convert it to Kelvin. All right? Because here, negatives don't work. This only works if this is absolute zero. So when we get into this right here, this is what I want you guys to do. If you guys are going to use these here, you have to change them to Kelvin. And how do you change this to Kelvin? Well, Kelvin, you got absolute zero, and then you got 0 degrees here. There's 273 degrees. So what I need you guys to know, write this down somewhere. 0 degrees Celsius is equal to 273 degrees Kelvin. I'll write that down somewhere. Let me, can I go insert? Thank you. Right here. 0 Kelvin. There is no degree sign there for Kelvin, by the way. It says 0 Kelvin is equal to 273 Celsius. Okay? That's what you guys need to know. So let me go to superscript. All right? So what if I said to you 25 degrees C is equal to what in Kelvin? How would you figure that one out? Well, 25 degrees is above 0. It's 1 degree Kelvin is equal to 1 degree Celsius. They mean the same thing. So you would go 273 plus 25 equals 298 Kelvin. All right, let's try another one here. What would negative 20 degrees C be equal to? So if 0 is 273 Kelvin, minus 20 would be 253 Kelvin. If you guys have any issues with this, hopefully there you guys have seen this all before. If you haven't, no worries. Shoot me an email. We'll get you squared away. All right? This one is not too bad. But you have to use for these Charles, Celsius, no worky. You got to change these there to Kelvin. So, and again, I've given you 1, 2, and 3. And asked you to find the volume here. So I've given you 3 out of 4. You plug and you play. Next question. Okay? Have a look at those. If there's any issues, let me know. Actually, you know what? Yeah. This is a good one. All right? And if you have any issues with converting to Kelvin, get a hold of me ASAP. Because you can't do any of this stuff unless you got this mastered. Once you do it a couple times, it should be okay, though. Again, same style question. Okay, so you guys can have a look at this. And I recommend you've got the question, you've got the answer. When you have some time, set this up. Because that's how you want to do this. And set it up right. See, you got your knowns. Because you're not going to have this on the test. Well, beside the question. So I'm showing this to help you to learn. That's why the formula is right beside the question. You will not have that luxury. So you will have to pull everything out. Okay? Get rid of the English. Okay, I got volume. I got temperature. I got another temperature. And it's asking me for a new volume. Okay, so that's got to be Charles' law. Scenario 1. This is scenario 1. So that's these guys here. And then scenario 2. Here, and plug and play, and away you go. Okay?
Sorry, Ian.
Yes, talk to me.
I think I maybe heard you wrong, but did you say 0 degrees Celsius is equal to 73 degrees Kelvin?
Yeah, right there. That's exactly it. That's what you need to know. That. Okay. Sorry. What 0? Did I have this in? I think I have this inverted. Sorry, I have this inverted.
Okay.
Sorry. No. Thank you for that. There you go. 273 Kelvin is equal to 0 degrees. And you think about it, the better if I had a whiteboard. You have a Kelvin scale and a Celsius scale. 0 Kelvin minus 273. So maybe I'll write that one down here too. Let's have a look. 0 Kelvin is equal to minus 273 Celsius. So this is what this is. I don't know who I was speaking to, but please ask questions. Sorry if I...
So then why wouldn't you do the 25 times 273? Because if it's 25 degrees and 0 degrees is equal to 273 Kelvin, why wouldn't you times that?
Well, it's all adding here. Like, if it's 12 degrees now and the temperature increased by 13 degrees, it's now 25 degrees, right? This is all additive and subtractive. And you have the absolute 0. That's where all the molecules stop. That's at 0 degrees Kelvin. But we generally use Celsius. 0 degrees Kelvin is equal to minus 273 degrees Celsius. Okay? So 0, absolute, and this is absolute 0. Talk to me. 0 degrees is minus 273 degrees Celsius. So let's say we bring this up to 0 degrees Celsius, the freezing point of water. How far have we come up? Say 0 degrees Kelvin minus 273 degrees Celsius. This is absolute 0. Now we're going to heat it up to 0 degrees Celsius. And that's now 273 degrees Kelvin. They work like that. Let's try one here. Let's just try one. Let's go to 143 degrees Celsius is equal to. So Celsius to Kelvin. What would this be equal to? How would you figure out 143 degrees Celsius in Kelvin? Well, what's 0 degrees Celsius? 273 Kelvin. That covers from to 0.
You add them together.
And that's exactly it. And then what number is over 0? I have 143 degrees that are over 0. So 143 K is equal to, I don't know, what's that equal to? Anybody know? 300,
416.
Thank you. How is that one? We could try one more. I don't care. Minus 50 C. Now, we don't have 273 because this is actually below 0. So, sorry, was that Aaron? Somebody there?
Yeah, it's 223.
273 minus 50 is equal to, you got it, 273. If you have any issues with that, come and see me. I'll do a short tutorial and we'll get you all straightened away. That one's easy peasy. And don't worry if you don't see it. Email me. We'll take it away. Okay? But being able to flip in between Celsius and Kelvin, you got to do it. Okay? So a sample of the CO2 has a volume of 200 milliliters at 20 degrees C. Okay, so I got volume, I got temp. What will its new volume be? So I need a new volume, and they've given me a new temperature. Okay, so that's Charles' law. The only problem is changing 40 degrees C and 20 degrees C to Kelvin, which in this case here would be 293 K and 40 degrees. Was that 293, 313? Okay. I wouldn't give you these in a test. You'd have to figure them out, but that's how she would go. And I've given you 3. You find the 4th. Again, another one here. Just for the matter of time, there's your answer. Y'all can try it out. And please do try it out. Okay? The volume of a gas always increases when? So the volume of a gas always increases when the temperature increases and pressure decreases. And you remember that? You increase the temperature. Why do you think they have a burner underneath a hot air balloon? Because you need that hot air expanding, keeping that balloon moving and flying and up, right? So the volume of a gas will always increase when the temperature increases and the pressure decreases. Gay-Lussac's law, look at this. All right. It's just kind of walking over the same ground. I don't even think I have a question here for you, but it's just kind of the same thing. Okay, like here, I will give you a Charles law. I will give you a Boyle's law, wherever the heck that one went. I could give you a Gay-Lussac's law. It's written on there, but it's just the same thing. It's pressure and temperature. And what do you have to do with the temp? You got to change it to Kelvin, right? Here we go. So basically, here are the 3 laws there that we just covered. And you see Boyle's law deals with pressure and volume with temperature controlled at the same. So the temperature for this situation is the same for this one. Charles' law, we're dealing with volume and temperature, but the pressure is kept the same. Gay-Lussac's law is pressure and temperature where the volume is kept the same. And we finagle these all around and look what we get. This is a good one. This is the one, this is one of the good ones here, okay? This is called the combined gas law. How many parameters do I have in here? How many unknowns do I have in here? 6. So how's it going to work? I'll give you 5. Problem solving. This I've kept in here for years just to verbally to see. But the best way to do these questions, is every question you have to reset. You never know what I'm going to give you. You want to get away from the English words as much as possible and get into mathematics. I know mathematics scares people, but it tends to be, what's the word? Unambiguous. There's only one vision. But, with written language there's different ways of interpretation, right? So let's have a look here. You're going to see this. And whenever you see this, it means 2 things. Remember there, I was telling you there that I'm going to give you 3 and you have to give me the 4th, or I'm going to give you 5. Okay, you're going to have to give me the 6. You will see this. And when you see it, I want your brain to go ding, 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 ding. Oh, he's giving us 2 things right there. That means 2 things. 2 things. 2 things. 2. All right? Standard temperature and pressure is just a lazy way of saying there that this experiment is going on at STP. It's a lot cooler, scientifically speaking, than saying this experiment is going on at 0 degrees Celsius or 273 degrees Kelvin and 766 milliliters to 1 atmosphere. All right? We just say this experiment is happening at STP. And that means standard temperature and standard pressure. And what does that mean? It just means the temperature is 0 degrees Celsius or 273 degrees Kelvin. Standard pressure just means that things are happening at 1 atmosphere. At this right here. Okay, so standard temperature and pressure just means I'm giving you 2 things that you will need. Okay, I'm not here to fluff you guys. If there's nothing to, I'm not here to try and trick you guys. Okay, the information I give you is the information there that you will need to solve the question. All right, so have a look at this one. This is a good one. Do I have animation for this one? I do. Good. So let's have a look here. I think you guys can still see this. Okay. So if a sample of air occupies 500 milliliters, okay, so I got a volume, at STP, whoa, that's 2 things. So I got 3 things now. I got a volume, I got a temperature, and I got a pressure, right? You know what those mean because they're written on my formula page, which it is. What is the volume? So I'm looking for a volume at 85 degrees. So there's a temperature and 560 torr. That's a pressure. So there's 6 bananas there. Okay, so it's got to be this one right here. So now, you see, I pulled everything out and I'm looking at it. There's my 500 milliliter volume that was there. STP, okay, temperature 273 Kelvin. We're not really, you could write 0 degrees Celsius here in your known section because this is on your scrap piece of paper, but you might as well get used to writing it in Kelvin. All right. Just before I tell you, I will come back to that, but you'll notice here for Boyle's law right here, there is no temperature. So there's no need for any type of temperature conversion. Temperature is actually remain constant. It's only for Charles' law, Gay-Lussac's law, and then now we're into the combined laws. Okay, so getting back into this one here. Here we are. So this is everything there that we know. The standard pressure is 760 torr. That's all P1, V1, T1. Here, P2, V2, T2. All right, and they've asked us there for the volume. So I'm looking for V2 up here. You have to write your formula, and flip it all around. Now, how do I do this? Here, I'm just going to come back to this here. There's your formula that you would have. And you see, I've got all this, I don't have V2, so I'm looking for V2. So I've got to get this divide by T2 out of there. Opposite of divide, times. So this T2 is going to pop up over here on this side up. P2, if I want to get rid of this one, because I want to get V2 by itself, it goes underneath. That's how, in a nutshell, that's how these guys go. Okay, so eventually you get your formula V2 is equal to this mess. Plug and play. Don't be intimidated by the numbers. And please do not plug this whole thing into your calculator at once. Break it into sections. 760 times 500 gives you a number. Times that by 358. You get a number. Write it down. That's your numerator. I have two numbers on the bottom that constitute my denominator. Multiply those together to get one number so that I have a numerator of one number divided by a denominator of one number. So now I can do that in my... Please don't do this with brackets and all this kind of stuff, and because I've seen it happen. Because it's great methodology, these multiple choice, it's either give me the right answer or you get zip. So give me the right answer. Don't let the calculator take it away. Have a look at this one. Okay. I don't know what happened to my animation here. But have a look. Sample of oxygen gas occupies these guys right here. So there's my V1, P1, and T1. Calculate the temperature in Celsius. So, and I give you this information here. So here's all the information there that I gave you. Okay, 25 degrees Celsius has been converted there to Kelvin. Ian, the horrible teacher, has asked me to calculate the temperature in Celsius. So that means at the end, I'm going to have to flip this back to Celsius. But the reason why I put this question on here is because we are looking for T2. It's this guy right here. People have problems with isolating variables that are on the bottom. If we're going to find a variable and its value, it has to be, it can't be it has to be greater than 1. So like if I just write the number 2 here, I don't know if you guys can see that or not. Just move this around. This number 2 is a real number. It's actually 2 over 1. Would you agree or disagree? That's 2 over 1 means the same thing as 2, right? That's a real number. But if I put that 2 under 1, now that's a half. Now I've changed things, and I don't want to change things. What's Ian talking about? Temperature here, that's what I'm asking you to find. It's on the bottom. So if I move this P2 over here, P2 here, if I move this V2 over here, okay, I can now solve for T, right? No, you can't, because there's still 1 on top. My advice for this one here, it follows the same as the previous. It's not a big deal. The only thing, if you're solving for T, and you will be because I'll put one on the test and on the quiz, if you're solving for T, before you do anything, take your formula, P1, V1, T1 is equal to P2, V2, T2, and flip it so that your T's are on top. Now solve for T. That's my only bit of advice, because I've seen good students make mistakes here. If the unknown that you're looking for is underneath the denominator, well, if you can flip it, and you can do it, it's okay. I flip one side, as long as I flip the other, this is a perfectly good equation. Okay, so what I did was I flipped both of these so T2 is on top. and then got rid of the P2 and the V2, and you end up with this formula here. Okay? If there's any issues with what I was talking about, shoot me an email. We'll get it all sorted out. And you see now you've got 5 bananas in here. You just plug and play. That's all it is. Okay? So you start to see these formulas there. You're kind of walking over the same carpet. Yeah, okay, there's more stuff going on, but it's kind of the same carpet. The only trick for that one, make sure, I will ask you for T, you've got to flip this. All right? It'll make things so, you don't have to flip it, but I'm just giving you guys an easy way out. Okay? Same question. There's your answer. Go. A sample of gas has a volume. Okay, so there's your P1, V1, T1. What will its volume be? So V2, we don't know. At STP, remember, 2 bananas. So Ian's given us 5. We need to find the 6. Okay? Aha! This is another one. This one here will be on your formula sheet. Okay? At STP, at standard pressure and temperature, so at 0 degrees Celsius, at 1 atmosphere, 1 mole of any gas will have a volume of 22.4 liters. Now, you remember there when we were talking about elastic collisions and kinetic molecular theory, and even though hydrogen gas weighs a lot less than chlorine gas is 70 grams per mole. Hydrochloric acid is 36.5 grams. Hydrogen is 2. It doesn't matter. 1 mole of hydrogen at STP, its gas will have a volume of 22.4 liters. 1 mole of chlorine gas at STP will have a molar volume. Sorry, what was that? Molar volume of 22.4 liters. And the same thing for hydrochloric acid. Any gas at STP, 1 mole of it will have 22.4 liters. So, what will my volume be at STP for 2 moles of chlorine gas? 44.8 liters. Would you agree? So if 1 mole is 22.4 liters at STP, 2 moles of gas will be 44.8. 3 moles of gas will be what? 37.2. You see how, again, all I'm setting you guys up for is you're going to do more boxes. Determine the number of moles in a sample of gas which occupies a volume of 1.52 liters at STP. This is the only requirement that you need to do this. If you do not have STP, you cannot do this. You cannot make that assumption, therefore you can't use this way. But if this is at STP, you know this, that 1 mole of any gas will have a volume of 22.4. So, now, since at STP 1 mole is equal to 22.4 liters, then make a ratio. My knowns, my volume is 1.52 liters, temperature is this, pressure is this. So you set up your ratio. I just took this right from here, 1 mole over 22.4 liters is equal to, what's the question asking? X moles over 1.52 liters. And you notice here, liters to liters, moles to moles. You could put liters to liters here and moles to moles here. It doesn't matter as long as everything is in sync. And you just, again, do a box, cross multiply, solve for X. There you go. Okay, so at STP, okay, we have 0.68 moles will have a volume of 1.52 liters. If 1 mole, 22.4 liters, this is 0.68, it's going to have less. Okay? So let's have a look here. this is all kind of the same thing. Choose the correct compound by finding its molar mass. Oh yeah. Let's have a look at this one. So, choose the correct compound. So over here, I've given you some compounds. One of them is the correct answer. Let's have a look. So choose the correct compound by finding its molar mass when 0.26 grams of a gas occupy a volume of 0.5 liters at STP. Same style question as before. Okay, since at STP 1 mole is equal to 22.4 liters. Okay, there are your knowns. 1 mole is equal to 22.4 liters. Okay, it's asking for the moles. It's actually asking for the molar mass, but we don't have it. Wait a second here. All right, cross multiply, you get your moles. And then you see, if maybe you think that this is your final answer, go back. Choose the correct formula by finding its molar mass. Whoa, molar mass? Sorry. How do I get molar mass from this? You guys have your triangle formula there. Molar mass is equal to grams divided by moles. I gave you grams here. I wouldn't give you anything really that is trying to confuse you. Okay? And this is from your week 1 formula there, even from last semester. Molar mass is equal to grams divided by moles. And we get this answer of 12 grams per mole. Well, which one of these guys here is 12 grams per mole? None of them, actually. Yeah, that's a mistake on my part. Why was I thinking that was 12? But anyway, I could change that. And the oxygen is 16. Sorry, I guess that should have been 18. But you see here, that's what you would do right here. You would get an answer of 18 grams per mole and choose this one here. All right. I'll clean that up there after and I'll repost it. But this is what we're talking about, is now I can start pulling formulas there from 3 weeks ago. And this is where I want you guys, organization is everything. And you see, I don't want you, and you look at these questions here. They are involved. And this, welcome to your test. All of your test questions are going to be worth 1 mark, generally, as far as I know. Okay? Just like they've been on the quiz and just like they've been on everything else. Go for the quick ones first. These ones here that are going to take 3 or 4 or 5 minutes, hit those ones last if you even hit them at all. Hit them all. But go for your short questions first because they're going to be worth the same as the long questions. So this is one of the questions there that you might want to leave until the end. Is there a question?
Hey, Ethan.
Yeah.
I don't know if I missed something, but you have the 18 grams per mole.
Yep.
How did you know that was H2O?
Well, which one here? Let's have a look. My numbers are off here. I don't know why I was thinking 12. I got to stop doing these at 3 o'clock in the morning. But so I got 18 grams per mole here. That's my answer. So what's my molar mass of O2?
You just add up all the masses.
Yeah, that's what we're looking at. And then the only one here that's 18 would be this one here. And that's how you would... This one here is a good question, man. This one here, just to kind of pull formulas all over the place, you're looking at 3-4 minutes at least, somewhere. And so, yeah, these are good ones. I think I have another one there. Good question. Anyone else got a question?
Why is it 18? Like, I typed it in my calculator.
No, these numbers are wrong. Originally, it was 12.
Oh, okay. That's
what it was. I'll adjust that. But I wonder if I can adjust it right now. No. But everything is the same here. So you find your number of moles, but then you go back and the question is asking for the molar mass. Well, I found out moles, but hey, Ian gave me this extra information here, and you would plug this in place. So let me have a look here. 18.0. Okay, so I'm going to change this right now to 6. Okay, and now that works. So I apologize for that there. You're just going in and you're doing your box. You get these moles here, and then you would incorporate another formula there. Moles is equal to grams divided by molar mass, and figure this thing out. Okay, difficult question. There's a lot going on here. Like, wow, we've got stuff going all the way back to week 3 or 4 of Chemistry 1008. You know, but decent question, fair question. Easy? Not really. Doable? Yes. All right. I'll update the PowerPoint there on Blackboard ASAP. But again, same question. What is the molar mass of a gas if 240 mils of that gas at STP? Okay. So I know maybe it only looks like there's one bit of information here, but there's actually 3. 240 mils of gas, and you got temperature at 0, and you got pressure at 1 atmosphere. All right. Has a mass of 0.320 grams. It's the same process. All right. So I left these purposely blank because I want you guys have the answer, you have the question. The question's not the problem, and the answer's not the problem. It's getting from this point to that point that I want you guys to try it out. And I put on here, see slide 31 for how these things are going to go. Okay, and I've added an extra slide because of my other slide there, but that's okay. We'll add this up right there. Okay. What else we got? Density. I think you guys have covered this already. All right, I've included it there in the week 1 as well as in the week 5. Did I include it here? Density is equal to grams per liter for triangle C week 1. And it's up in here. Okay. All right. So calculate the density of 1 mole of nitrogen gas at STP. How am I going to do this here? Calculate the density of 1 mole of nitrogen gas at STP. Well, density, you go and find your formula density, and hey man, there's no moles here. Density is grams divided by liter. Okay, calculate density of 1 mole at well, how do I get grams? How would I find grams? How much does this weigh? Well, it's 1 mole of nitrogen at STP. Since there's no grams, I got to stop for a second. And grams is equal to the number of moles times the molar mass. Well, I told you there that there's 1 mole of nitrogen gas. What's my molar mass? Well, nitrogen is 14. And there's 2 of them, so it's 28. So 1 mole of nitrogen gas at STP there weighs 28.02 grams. Now I can substitute this back in. Because this is at STP, I know the literage. It's 22.4. So there's my density. So you see, now we're playing around. And as I said, you're going through these questions, you don't know what's going on from one question to the next, so you kind of have to reboot. You look at this one, calculate the density. Okay, so you find you have one formula for density. That's what you're using. Density is equal to grams per liter. Wait a second, he only gave me moles. But he did say it's at, if you see at STP, use it. Okay? And how do I get grams? Well, I've given you moles and you have the molar mass. You always have that molar mass, okay? So, good questions. This is it. This is the end of the game. All right? We got about 5 more slides and then that's it. Which of the following gases is the most dense? Well, now that you've seen the question, I could ask it to you, but you just look, which one is heavier? What's going on here? Hydrogen gas, pretty light. Nitrogen gas, again. But CO2, if you know there, we use it in fire extinguishers because it is pretty dense, it's pretty heavy, and it kind of disperses oxygen out of the way. That's what a fire extinguisher does. It gets on top of, it forms a layer. Here's your fire, here's your carbon dioxide, and here's your oxygen. And if the oxygen can't get through to the fire dies. And that's the whole point, right? So the answer there is carbon dioxide. Aha. All right, let's have a look. So, welcome to a new one. And I did say that this was kind of formula heavy. All we've been talking about there is STP and these kinds of things. Here's another formula. Okay, here is pressure times volume is equal to the number of moles. Yes, we use M, small m for moles, but this one here, small n, is number of moles. So PV is equal to nRT, where T is the temperature, but R is a constant. So in this formula, it may look like there are 5 bananas in here that you will have to solve for, but there's not. There's only 4. P, V, N, and T. R is a given. Now, if you are using atmospheres for your pressure, then you must use this R value. If you are using kilopascals as your pressure, then you must use this R value. That's the only trick. Calculate the volume of 1 mole of any gas at STP. Let's have a look. There's your formula. We already know what is the volume of 1 mole of any gas at STP. We already know that, 22.4, right? But let's have a look at our PV is equal to nRT. What is the volume? Okay. Number of moles, R value, temperature, and pressure. So 1 mole is equal, what's my R value? Well, what's my pressure value? It's in atmosphere, so I have to use the atmosphere one, which is this one. So N times R times T. See that, Kelvin? Don't use Celsius. It's only Kelvin. And atmospheres here. So you must use the R value if using atmospheres for P. And there's your value, 22.4. So this is a good formula. Difficult formula? No. But you will have to flip it around. And the trick to this is R. You would get the same answer if you used, okay, the other R value. It just means that your atmosphere would be different. Okay, a different number. And this is what we call the molar volume. Okay. Here's another one. Let's have a look. How many moles of argon are contained in 1.3 liters at 24 degrees Celsius and 740 millimeters of mercury? Ugh. How many moles? Start pulling these things out. What's happening here? So here are my knowns. Here I got a volume, a pressure, a temperature. All right. And it's asking me for the moles. So we have been talking about moles and gas. This formula here is the connector. Okay? Because this is not at STP. We use this formula generally when it's not at STP. We use this way. Sorry, I'm coming to it. Where is it? We use this way if it is at STP. So at STP, we use this simple ratio there with this information. Okay, do the simple ratio to find your moles in gas at STP. If it's not at STP, moles and gas, we have to use this formula here. Okay? I'll say that again. If you're trying to find out moles with a gas at STP, use your ratio. 1 atmosphere is equal to 760 million, is equal to 101.3 kilopascals. Okay, and you do a box, easy peasy. If it's not at STP, moles and gas, you use this one right here. PV is equal to nRT. Okay? And same style of question. It's asking for the moles. So here you flip your formula all around. See, you want your N by yourself. Get rid of your R and your T. Get it out of there. And that's what we get here. Plug and play. Okay? Yeah, there's still a couple more. Same style of question up until here. But then I give you an extra little question here to find the molar mass. So everything is the same. Look, N is equal to PV over RT. Everything is the same to here. But then I've given you an extra little bit to find the molar mass. Okay? So,
Ian?
yes, what you got?
Sorry to interrupt you.
No.
What does the N stand for again?
Moles. Yeah, you go to your formula page, and generally moles we use a small m, right? But here in this particular formula, I didn't make the formula. If I made the formula, I swear I would put an m. But this one here is just moles. It's exactly the same moles as this right here.
Okay.
Got it?
Yeah.
Okay. No, good question. Thank you. So that's that one there. It's exactly the same procedure as the previous, except for this right here. I'm just asking you to throw in another triangle formula, which I'll do from time to time. Here's another question. Okay. Have a look at all these. And that's the only mathematics. It's just repetition. Do it again, do it again, do it again. And then time number 2.5, you won't need to do it again because you got it, right? So same question, there's your answer, go get it. You remember this one? Maybe you don't. It's way back in week 1. I think somebody said in the comments there section, week 1 seems like a million years away. Sure it does. And we're going to get back into this in the same way. It's really nothing too different. You convert between moles and volume using molar volume. This one here at STP, write that somewhere down. That one there is king bananas, I tell you. If at STP, it's 2 bits of information, but it also unlocks many doors that makes things a lot easier, because 1 mole of any gas at STP is 22.4 liters. Okay? Use the ideal gas law. PV is equal to nRT if it's not at STP. Okay? So, what do we got here? Calculate the number of moles of phosphorus needed to react with 4 liters of hydrogen gas at 273 Kelvin in 1 atmosphere. Holy smokes, what's going on here? Well, I've got a chemical equation, so you know what? This is at STP, because this is 1 atmosphere and 273 Kelvin. I know those. So I have STP conditions here. So that means that I can do things there that I couldn't do before. All right, so there's my molar ratio, 164. Okay, it's asking me calculate the number of moles of phosphorus. So X moles of phosphorus are needed to react with 4 liters of hydrogen gas. Well, what, 4 liters? Hey, wait a second. This is moles. This is moles. This is moles. Can't have liters in here. Okay, I need moles in here in order to do my box. Well, because this is at STP, there is a relationship between moles and volume. Okay? And that's what this is. Since at STP we can use this moles in volume. So to find the moles of H2, because I can't do a box unless I get this to moles. So 1 mole is equal to 22.4 liters. X moles, because my moles are on one side, is equal to 4 liters. So 4 liters is how many moles? Right here. So now you have moles. Sub it into the box. So now you've got your box. You've got 1, 6, 7, and X. Cross it up. There you go. Is that my beagle? All right. And this question here, it's just about recognizing certain things. Okay? That can make your life a lot easier, because if you didn't see that, things might get a little difficult. Okay. Same question again, same style. Okay, what volume of O2 at this pressure and temperature are needed to react completely with 3.2 grams, okay, of ethane? You see grams here, it's no good. You know that you're going to need some moles. You've got your molar ratio there. Fill in what you know. Here I've got liters. Here I've got grams. I don't have STP. I'm looking for volume here. I need to change this there to moles to find the moles. There are your moles there. Now you can plug this in, and same as you did there week 1, and away you go. Okay. And I want you guys to try these out, and some of them there are going to be a little painful, but you know, you could even print these off and have them by your side, like this open book test. I don't care what you guys use, as long as you know you're not hacking into somewhere to do it. You guys have these things, have them printed out step by step. It's all logistics, knowing where to put things. Oh, someone's not happy downstairs. Oh well, that's all right. Now I want you guys to try these out. Oh God, they're coming. Save me. All right. But there is one thing there that I do want you, again, same style question. Try these out. Okay? There's no other way to do them other than try them out. Again, same style. No different. Dalton's law of partial pressure. This one here is easy peasy. When you, like when I was in the Middle East there, a big thing there was the shisha pipe. And, you know, you would smoke the tobacco and it would go through the whole contraption, and then it would go up under water, and it would bubble up through the water. Okay, and, you know, that would be your tobacco. Well, when you gather gas over a water, or a water over water, the gas picks up some water. And now within that, you've got pressure from the smoke, you've got pressure from the water, and together they make an equal pressure. That's all this thing is telling you. And you'll see how silly this question is. I'm just going to show you the question. A sample of oxygen is collected over water at 22 degrees and 762 torr. What is the partial pressure of the dry oxygen? Because you see, a sample of oxygen is collected over water. That means it's wet. It's got the water in it. So a sample of this oxygeny water is 762 torr. Okay, what is the partial pressure of just the oxygen? Well, you can't figure it out unless I tell you what the pressure of just the water is. So I'm asking you to find just the pressure of the oxygen. I give you the pressure of the water. You subtract the two, 762 minus this guy will give you this. So that's what this formula is right here. The pressure of everything is equal to the pressure of this, plus the pressure of this, plus the pressure of that. it's pretty not too bad. Okay. I apologize. That's long, and I know it's tough, and you guys are tired of looking at me. But do you guys have any questions? That's what I got. That's the course in a nutshell. I've left these things blank so you guys can go and try them out. As far as I know, there's nothing due other than the assignment there. And next week there, Lab 3 and Quiz 3. Okay? And Quiz 3, take it seriously because I haven't tested you on this week's stuff or last week's stuff. So, and that's where the focus is going to be on there for Quiz 3. Only this week, week 5, and week 4. I'll send an announcement out and all that. But that's what I got. And if you guys don't have any questions, get out of here. I'll post this there to YouTube, and away we go. I don't even know if you guys are still here. Okay. How we doing?
We're here.
I know. It's not easy, guys. It's not easy. But this is it. I'm asking you there for... Go and try some of these. Some of them will come easy. Some of them will not. But please know that I've done this there before, and trust in me that everything will be out. We have an extra week now. So you guys do all you can until the next time we meet. And then now you guys are going to hit me with questions. Continue to email me. And trust me, in 2 weeks there, you guys will be rocking and rolling. Okay? That's it. Get out of here.
I have one more thing, Ian.
Yeah. If anyone has any questions, just stick around.
It's just about, do you have any, recommendations for what questions we should do in the textbook?
Yeah. I give you questions every week. Do you see those?
Well, yeah, I see those, but then it's if I do the reviews, it's only a portion of the reviews on those questions.
Yeah.
So the rest of the review question is completely different.
Oh, well, they all kind of employ the same skills. Your test stuff will be multiple choice. So that's where we're looking at. So
okay, so everything that the questions you provide is basically what we just have to look at.
Basically I'm saying look at everything. That's the best answer I got. But I'm sorry, but yeah.
Okay.
No, the style will be multiple choice.
Okay.
But do try those questions there at the end. They're in the syllabus, I think, and I give you the answers there. Okay. And they're all in the syllabus. Try those ones out because they're good little practice. And these ones here in the PowerPoint, I left them blank. Just because I want you guys have the answer. You guys have it all. These ones here, I left them blank. Hit them. And if you can't hit them, then these are the things there that we'll do there next week. Okay?
Okay.
Rock and roll. Thank you so much.
Alrighty, have a great night.
You too. Who else?
Okay.
Take it easy. Anyone else? What do we got?
Would you be able to do the first gas stoichiometry one that says your turn? I tried it, but
this one here? Yeah, I couldn't do it here because honestly, I swear to God, that took me about 40 minutes. I hate organizing MS Word documents or gas, but yeah, this one here, you're just going to follow it kind of the same thing. I know it looks, but if you can turn on the animation, you see here, kind of goes step by step. And this is how I want you to do this. This is crazy important. What information did I give you? What are you looking for?
Okay.
Can you see that? Am I still sharing?
No.
Oh, well, yeah, that's not good. Then let me share. There. So, I'm just going to go back here and from current slide. So you see here, for this question here, this is what it'll look like, right? Here's your question. I'll give you the chemical formula or a chemical equation. If I don't give you the chemical equation, you can curse my name because that's a heck of a lot of work. And, but you see your molar ratios, you're still going to need those. Okay. And because I've pulled out everything out of the question, what did Ian give me? What is he looking for? Well, he gave me pressure, he gave me temperature, he gave me grammage. All right. I'm looking for the volume. Okay. And if I ever give you these guys here, I've given you the molar mass as well. Just a little thing there. Just something as silly as that. I've given you the molar mass. So, and I'm going through all this here, and I got grams here and liters here. Well, it ain't good because this is all moles. I need mole here to do a box. So, I give you 3.2 grams. You've got the molar mass here, okay, which you just find with your periodic table. And there you go. You've now found 3.2 grams of this, of ethane, is equal to 1.1067 moles. So now you can plug that guy right in there. So now that is 0.1067 moles. All right. So now you've got moles, moles, moles. You can do a box, find moles over here. Got it?
Yeah, okay, I did do it right then. I just forgot to multiply it by
Good.
2 moles.
You know what? That's great. What an awesome mistake. Because you learn from it. And make mistakes. Now there's no mark. Make as many mistakes as you can. I think it's great. And so you found that. And then you do your box. You found the moles of oxygen, which is right here. Sorry about that. And then what is it asking for? It's finally asking for volume. And then you would use this formula here because we don't really have volume up there, and you'd have to use that one there. But try these out. They will click. It's just you got to put in a bit of time, that's all. How are we doing, Kaylee?
Good.
Okay, you keep at it. And I don't even know if there's anyone there. Is it just me and you, or what's going on?
Yeah.
All right. Get out of here and enjoy your day, and keep in contact, please, okay?
Okay, thank you.
Okay, later, skater.